Hello, everyone, and welcome to another workshop for the ICP Bitcoin DeFi Bootcamp. So your usual host, Rebecca, is away traveling for the Token 2049 Singapore conference. So if you are in Singapore right now and you're watching, please feel free to go and say hi to the Encode team over there. I hope you all have a great time if that's where you are. But today, I won't keep you for too long. You've got me, Blake. I'm a member of the Encode team. You might see me in some other boot camps. And today I'm going to be introducing Christopher to talk about vetKeys and how you can use them to create and transport cryptographic keys. So yeah, by the end of this, you'll have a clear understanding of them. And I look forward to hearing this workshop from Christopher. So I'm going to invite him up onto the stage now, and he can come and share his screen and deliver his workshop to you. Yeah, please say hi in the chat. And as always, please feel free to ask questions as the workshop goes on. Hi.
Hi, everyone. I am Christopher, developer evangelist at Dfinity Foundation, and I'm happy to be here talking about vetKeys. vetKeys is one of my favorite topics, one of my favorite features that we have launched in a long time. But before I start, could some more of you just post something in the chat, like a 1 or whatever, just to give me some sense about how many people I'm talking to and if there are any people present. So hi, Emmanuel, Kasia, Analia, Antoni, and the rest of you. I'm going to share my screen and we'll dig right in and talk about vetKeys. So share screen, window, and there it is. vetKeys is an acronym that stands for Verifiably Encrypted Threshold Key Derivation, which is a kind of a long, complicated term, but all of those parts actually have meaning. And in this presentation, I would like to share with you not a super low. We will most likely not go into code. So we will stay at a slightly higher level, describing starting with the overall concepts, and then I will show you a showcase application that demonstrates 3 different uses of vetKeys, how they can be used. But we're starting with the high level overview. So vetKeys, verifiably encrypted threshold key derivation. And one of the long-standing challenges when it comes to blockchains and open decentralized networks is that how do we store secrets, right? Because the blockchain and the network is open, so that is really one of the core challenges, one of the sort of the holy grails to solve when it comes to blockchain technology. Because if you want to, for instance, do some enterprise use case, or maybe you want to build an application that actually works well with the EU regulations and the GDPR regulatory framework, then of course you cannot have information out in the open, because so usually that is where every conversation with an enterprise person stops, when they realize that you can build on blockchain technology, but by the way, all your information will be out in the open, and then they stop listening, of course. So vetKeys is a technology that allows us to solve this challenge. So we want to encrypt information and store it on the blockchain. So it's not the blockchain itself that encrypts the information, but we want to be able to, in a secure way, generate an encrypted key to encrypt any kind of information and then store it on the network. And once we have stored it, we want to be able to retrieve that information again, right? In a secure way. On another device, even. without having to do any key sharing or anything like that. So that was the first challenge. Another challenge we want to solve, that is also a long-standing challenge, is that, okay, if we figure out how to encrypt information, how do we encrypt the information for another user? That is an even more tricky problem. Because in order to encrypt information for another user, I need to figure out that user's private key, and how do I get a hold of that private key without, public key, without doing some kind of key exchange in advance. So you can do the key exchange, and many applications do in some kind of handshake or key sharing or whatever. But that whole process is a bit messy, right? So if I want to send a message to a user that I have not been in contact with yet, then I don't want to have to do this key sharing ceremony. And vetKeys solves this issue as well. So we can encrypt information for another user using some identifier, some arbitrary identifier as ID, and then we share this information with that user that then can securely decrypt the information. And that we call identity-based encryption, or IBE. So when we unlock on-chain encryption in this way, we unlock a whole range of super exciting use cases, right? We can do end-to-end encrypted messages, we can do secure file storage, we can do, I've listed a number of stuff here, that privacy preserving voting, secure auctions, games, like different kinds of bidding games where the bids are closed until all the players have completed a round of the game, and so on. But let's look at how this all works. So in this overview, we have three parts here, three main parts that are involved in all this. We have the front end, that might be a React, or this is just a regular HTML JavaScript front end. We have the canister that does a big part of the work here, and then we have the subnet of the nodes in the ICP network that actually does the key generation. So the nodes, as you might be familiar with, the ICP network consists of subnets, a number of subnets, and each subnet has between 13 to 40 nodes. And on these individual nodes, they hold what we call a master key share, or a small shard of the master key required to generate these encryption keys. But one important thing here is that no single node has the full master key. And it could be said that the full master key never really exists. No one has ever viewed the full master key. Instead, we employ what we call a threshold signing algorithm, where these nodes together sign. They sign using their key shares, and when the signed bundles that the nodes produce are put together, then we get the final signed. The bundle that is signed with the master key, so to say. And this allows for up to 1/3 of the nodes. Our current implementation allows for up to 1/3 of the nodes to be offline or malicious and so on. And the algorithm is still working. So it's quite fault tolerant and tamper proof. So when we want to encrypt and save some data, we rely on the subnet nodes to derive an encryption key for me as a user. And when I derive the key, I use some derivation path or ID as the identifier for this key. And this allows me to generate or derive any number of cryptographic keys for an individual users. And this derivation ID might represent anything from a user ID to a time. When we do time lock encryption, that ID instead represents a point in time, for instance. So the subnets in the node, the nodes in the subnet, they can derive cryptographic keys by signing information together. But the question is, okay, now they have generated a cryptographic key, an encryption key. How do we transport that derived key to the front end? Because me as a user, in order to be able to encrypt something, I need to get a hold of that key in a secure way. And you know, who would I trust to transport this encryption key from the nodes in the subnet by way of the canister to the front end? And the answer, of course, is that I should trust no one. So instead of trusting someone, we do it like this, that we, in the front end that wants to derive a key, you create what we call a transport key pair. So the green and the yellow keys there represents a private and a public key that then will be used to encrypt the generated key for me. So what I do in the front end, I send my request to the canister saying I would like to derive a new cryptographic key, and in that request, I submit my transportation key, the public key. The private key I reserve for myself to use later when I want to decrypt the information I get as a response. The canister, in turn, asks the nodes in the subnet to derive a key for the user on behalf of the user, and uses the identifier that I specified. That might be any identifier. So there I list it might be a user identity, an email address, it might be an Ethereum address, whatever. So the canister asks the subnet to generate a key with this identifier and encrypt that key with this transportation key. And we have a question here from Adam that I might be able to respond to directly. Can a node possibly be part of more than one subnet, or it's specifically assigned to on a single subnet and not able to part of another? Yes, a node can only be part of one subnet, but so the nodes make up the subnets. Yeah. And a canister can also only belong to one subnet, but canisters can communicate across subnets. Of course, there's a slightly longer latency when you do cross subnet communication compared to doing communication inside a subnet. But that essentially gives ICP endless horizontal scaling. When we hit the ceiling of what ICP can deliver in terms of scaling, we can just add another subnet. So encrypt and save some data. We getting back into the game here. The canister have asked the subnet and the nodes in the subnet generate a cryptographic key for me with this identifier, use it and encrypt that key using this transportation key. And here's a neat trick is that the key is encrypted at creation. So the nodes in the subnet also never have access to this cryptographic key that we then want to return to the user, but that happens as part of the key derivation process. So then the subnets together, they return this now encrypted cryptographic key to the canister, and the canister can in turn safely return this encrypted cryptographic key to the front end, where I can use the private key I generated in the first step to unlock the encryption key, and boom, there I have now a cryptographic key, access to a cryptographic key in the front end. And from there on, it's fairly straightforward. Once I have access to the cryptographic key, I can do anything I want with it, and by anything, then I mean I can encrypt data in a number of ways for any number of use cases. So I use my encryption key, I encrypt some data, I just store this encrypted data to the canister. And that's it. That is the first part of the process of creating an cryptographic key, encrypting something, and storing it in the canister. The second part of the process, of course, is the reverse, so to say. Then that is decrypting the data. And here, the good thing is that we just run the process again. But sort of in reverse, I have the encrypted data. I create the transportation key. I ask the canister to derive my key, or maybe I have just cached the cryptographic key since last time I used the application. So it all depends on what kind of security profile you would like to have in your application. So, for instance, if I want to just store some information for myself personally, and it's not like super sensitive information, like imagine you creating some simple Dropbox clone-ish thing, then on first, when I first sign into the application, I would generate my personal encryption key, and then I would most likely cache that in the browser somehow, so that when I log in the next time, I will just reuse it, because deriving these keys come with a slight cost, because it involves this threshold derivation process where all the nodes in the subnets are involved in this fairly complex cryptographic algorithm operation. And that was the end of that first part of the presentation, and I think I will switch screens right now, and I will hop over to the demo part. So 1 second. Closing that one. Share window. So here on the screen, you see the vetKeys showcase application. And this application is an application that showcases 3 different ways to use vetKeys. And just briefly describing them, the time lock is, or let's start with the simplest one, I think, is the encrypted note. And the encrypted note is I just encrypt information for myself. That is, I derive a key, a personal key for me. I encrypt some information, store it, then I can decrypt it. That's it. For the time lock, I'm using a similar approach, but there I, instead of just using my personal encryption key, I use the a point in time in the future as sort of the identifier, and then I let the canister decrypt the information when the timer has been reached, or the time lock has, it's time to unlock it. And the third variant is a message where I use the username of another user as the identifier when I derive the key, and then I send them a message. Let's start with then okay, time lock is apparently the one we should start with. Time lock. So I'm going to log in, just a simple login without username or without password here. I'm logging in as Pam, and you see they're getting vetkey. So now in the sign-in process with this application, as soon as I sign in, it gets my personal encryption key using this process that I described already. And then but that we don't need that encryption key actually for the time lock. So time lock, we say hi time lock, and we set the release time to 10 seconds, encrypt and lock. The clock ticks down, and in 1 second here, I should be able to press this button, to unlock the time lock, and then the message is available again. And so now this is a bit of a, I'm going over this again, as all good teachers should do. Repetition, but in slightly more detail in this time. How does this time lock work? So it works like this. Me as a user, can I turn on this red dot? No, I can't. Me as a user, I interact with the front end. I basically call a React hook to create, let's say, create time lock. That is the first thing that happens. And after that, that React hook in turn calls the backend and gets the public key of the canister. The public encryption, so the public vet key for this canister, and that means I use no derivation ID at all. And the canister in turn asks the IC CDK, which the canister development kit, which is a representation of interacting with the nodes of the ICP subnet. So it returns that public key, and then I take that public key, and I use the vetkey support libraries that we offer for front-end development. So I say I would like to encrypt some information. I encrypt with the public key of the canister and the release time. And then I call the canister again to send the canister this encrypted data along with the release time. So that is the creation part of things. And then when the timer has reached 0, I call another React hook that says open time lock. That hook calls the canister. And now this is the happy path, right? So we are assuming that the time lock actually has reached 0. So if this would have been the sort of the unhappy path of me calling this endpoint before the time lock has reached 0, I would get an error instead. The canister then uses the other system function here of deriving the actual private key. So now I'm actually allowing the canister to derive the private key needed to decrypt the information. In the first step, I just retrieve the public key of the canister. So in order to encrypt the information, I only need the public key, right? But to decrypt the information, I need the private key. In many cases, you don't want the canister to derive the private key because the state of an ICP canister is not inherently secure, right? The canister runs on an open network, and one of the nodes running the canister code could be malicious. So in theory, the node could tap into the state and the memory of that canister and actually read the private key. But in this case, it's totally fine, right? Because once the time lock the timer has reached 0, this information is it's not a secret anymore. So then for this case, it is actually fine for the canister to derive the private key here. And once it has derived the private key, it can deserialize the information and decrypt it, and that we encrypted in the first step, and then return the unencrypted information to the client. So that is the first use case, how we use a point in time as sort of the IBE, the identity-based identifier in this case, and let the canister decrypt information. So let's see, the second example we should look into is the encrypted note. And this one is even more straightforward. Encrypted note, I have a small text box here, and I press encrypt and save. And then the interface says you have an encrypted note. And when I click here, that is information is decrypted very quickly, and yeah, you see the text there again. So this part of the demo actually uses that private key, that encryption key that I generated just as soon as I signed into the application. You might have noticed that when I signed it says getting a vetkey. So that is quite straightforward. Me as a user, I call this get user key React hook that in turn generates this random transportation key. So the transportation key is not, we can throw that away once we have used it. So it's just used during the key derivation process. And once I have access to the encryption key, I can throw that away. So I generate a random transportation key. I call the canister endpoint function saying, here, I would like to get the user key, the sort of the private key for this user and encrypt it with this transportation key. The canister, in turn, of course, the canister does some validation here, and that is important. The canister always acts as a gatekeeper, determining who can derive what key. So in this case, the canister will look at, that is why I have to first sign in to generate an IC identity to interact with the canister. So it first verifies that, I can only derive the key for myself and no one else, right? But once it have verified that, it calls, again, the Internet Computer Canister Development Kit, saying I would like to get the user key for username X, or Pam. I would get the encryption key for username Pam, encrypted using this transportation key. And that is returned to the user, where I can use that information to encrypt this node. And it's important to stress here that all encryption here happens client side, right? So the canister never has access to the encryption key in this case. So I save my note, called the React hook again, say my note. It encrypts the data using my encryption key, and basically just saves the encrypted data to the canister. And of course, in decrypting the information works very, very much similar. So let's look at the third and final example. Now we have used an IBA identifier using the time lock. We used a point in time as the IBA identifier. And the second example, we encrypted information strictly for ourselves. And in this third example, we will use the public key of some other user to send them a message, showing that we can avoid this whole hassle of doing this key exchange that you normally have to do on other platforms. So we have the messages here. Let's compose a message. I'm signed in as Pam. Let's send a message to Sam, saying, hi, Sam. Encrypt and send. I have sent this message. It's there in my outbox, so to say. And now I will sign out and I will sign in as Sam. So I'm signing out, signing in as Sam. And you see here, getting user vet key again. And you see there, I have something in my inbox. Message from Pam. I click decrypt and she says, Pam says, hi, Sam. And that is, let's have a look at how that works. And the key thing to stress here is that, we avoid this whole headache of having to do a key exchange. Which actually is a very big blocker when it comes to building apps that use encryption, because it's unclear where and how you should exchange these public keys. So again, me as a user, I interact with the React hook saying I would like to send a message. The message is something, and so in this case, I would send a message that says, hi, Sam, to the recipient, Sam. the React hook again gets the public key of the canister. In order to be so, one cool thing here is that I can derive the public key of any user. In this case, I can derive the public key of any identifier directly in the front end, just as long as I have access to the public key of the canister. So what I do here, the React hook asks for the public key of this canister on this subnet, and the canister in turn requests that public key from the nodes in the subnet, returns it to the client. This is uncontroversial. This is not secret information or anything, so nothing here needs to be encrypted. It's just a public key. And then I use, again, these front-end support libraries to encrypt some data using the public key of the canister together with the IBE identifier of the recipient. And that is where the sort of the magic happens. And in the time lock example, I instead used the public key of the canister together with a point in time. So that was an integer number. In this case, the recipient is just a string saying Sam. That is the identifier. And once I have encrypted the message with this IBE identified public key, I just call the send message endpoint on the canister, and yeah, the canister stores the message for me and for Sam. And I don't think I have another slide for that. So you can imagine how the process looks for them decoding the message that Sam, that actually works exactly the same. Like here, I get my own, to decode a message that have been sent. I just get my own personal private key, my vetkey, and then I decode the message that I have received. I think actually this takes us to the end of my presentation. I've been saying keys and vetkeys and private key a lot. I hope this all makes roughly sense. But again, to summarize what vetkeys makes possible, it makes it possible for us to generate a cryptographic key in a secure, decentralized, verifiable way, and then encrypt this cryptographic key and transport it safely to the user, where it then can be used for any purpose. And these are some fairly major unlocks in the decentralized blockchain space. So basically, I'm super excited about the possibilities of vetkeys on the ICP. And Anthony, to answer your question, seems like this can be used to create an encrypted order book. Yes, you're very much correct about that. So it's a good way to prevent front running of various kinds. You let the order book, all the orders be encrypted until a point in time where they are all unlocked and handled in the correct order, for instance. That is a really good use case. And Z says, I would like to see this on social posts. Messengers are too overrated. Yes, end-to-end encrypted messages, like the simple example I showed you in the showcase, is a really obvious and exciting opportunity using this.
Great, yeah, thank you very much, and thank you, Christopher. That was really good. I really enjoyed that workshop. And yeah, thanks guys for your questions. If you've got any other ones, please put them in now. Otherwise, we will end this workshop. And as always, if you've got questions, please feel free to ask in the Discord, and we'll all do our best to answer them. So
can we post links to these to the showcase application, for instance?
Oh yeah,
in
please.
the chat here.
Yeah, please do. Please do. If you post them.
Let me check and stop share screen here. VetKey showcase. This is the application. It should be really straightforward to build and deploy this. I'm posting the link here in the chat.
Excellent. Thank you very much. And I will also repost that in the Discord shortly after we end this workshop. Yeah. Okay. Yeah. Thanks again. Looking forward to seeing you guys again later this week for the next workshop. And yeah, see you soon.
Great.
Thanks,
and great tip, Esther. Check out the Diode and OpenChat. The Diode is one of the first projects actually using this in production, and they have a really cool way of using VetKeys. So check them out.
Great. Thank you very much. Goodbye.
Goodbye, everyone.